As you can see, if I change the gains for the PID in angle of attack, which is the integral path in angle of attack, the proportional path in angle of attack, and pitch rate, which I'm using to mimic derivative gain in angle of attack. It's not one-to-one, but it's close in this case. We have, you can see that mainly the closed loop in the range of frequency of the short period is moving, which are this one. So for example, if I increase the gain, the pitch rate, I'm increasing the damping and also the frequency of this pulse here. If you want to see a step response in angle of attack, that is like a first order response, the controller regulating perfectly the angle of attack. This is clearly not the case here, because you can see that the phugoid, it's really messing up. If you put a slightly low gain in the speed, in the true airspeed, now you can see that you have a step response in angle of attack that it's at least in short term, it's similar to a first order kind of response, but then in steady state you have a clear phugoid, lightly damped. So let's increase kV just to have some damping close to 0.7 as well, and you can see that right here, if you increase kV a bit more, you are not improving the damping, as you can see for these two little guys here. If I go beyond 0.7, 0.007, you're not improving the damping anymore. So basically this is, roughly speaking, how looks like the angle of attack controller for conventional and commercial aircraft. The other thing that I'd like to mention here that I think it's also super cool is that it's possible to use these widgets to make sensitive analysis, and I provided an example, a simple example here. This one is a slider with two controls. You have an upper control and a lower control, you see, and this establishes a range, and you can slide this one. What I did is that for this range, by separating 4 gains, which is this 4 gains here, for example, you go from 006 up to 012, and I put 3 gains in between, and I show here how the feedback of these gains is showing up in those plots. And this is cool to see the tendency, and this is it looks like even like it's a kind of root locus here for this first plot, because you can see how the increase of the gains is changing the pole positions for the closed loop. It's super cool as well. This can help a lot if you are designed for a single condition. You can see how this kV is changing even your short period poles. So okay.